I'm Maddie Cuff, New Scientist's environment reporter.
The temperature in here right now, -15.
Cool. I'm embarking on a scientific quest to discover the secrets of that most festive weather phenomenon, snow. Oh! And undertake an audacious challenge to make the biggest snowflake possible. It's Christmas time, so I'm getting all of my Christmas decorations made ready for display. And what's more Christmassy than a snowflake? But making these paper decorations really got me thinking, what is a real snowflake? How are they made? And can we get snowflakes this big, or even this big? Well, New Scientist has set me a festive challenge to create the biggest real-life snowflake I can. Across the globe, about 1 billion snowflakes fall each second, but some estimates suggest that about half the world's population have never seen snow close up. So, how big is the world's biggest snowflake? Okay, GuinnessWorldRecords.com, largest snowflake. The record was set in January 1887 in Clark Fork River Valley in the United States. And the snowflake was 38 centimetres by 20 centimetres. That seems massive. That's 38 centimetres. That's like a snowflake the size of a dinner plate. This can't be right. The website also mentions the world's biggest snow crystal, which was recorded by Kenneth Lebrecht in Canada. He's a physicist based at Caltech and has perfected the art of growing snow crystals in his lab. I dial him up on a video call to find out more. Ken, hi. Thank you so much for making the time. It's great to speak to you.
Good.
Could you just clear up what is the difference between a snowflake and a snow crystal?
So a snow crystal is a very specific thing. That's a single crystal of ice. But when you go outside into a snowfall, you sometimes see these puffballs falling. That's just a bunch of individual snow crystals that have stuck together. And those are called snowflakes.
Can you talk us through the physics of how a snowflake is actually formed?
Really nice stellar crystals that you think about when you think snowflake, those only fall under really precise conditions. And the temperature needs to be right around -14 Celsius, give or take a couple of degrees. When a single water droplet freezes, then it turns into ice and starts to grow. But not all the droplets freeze, and it grows by absorbing water vapor, and that water vapor is supplied by the droplets. And so it takes like 100,000 droplets to form one large snow crystal. And for the water molecule, it has a six-fold symmetry. And so as it grows further, you've got a little hexagonal plate, and the corners of the plate, they stick out a little further. And so as it gets bigger, those tips will grow faster, and then it will sprout branches. And as it grows, it becomes sort of a dendritic shape. There's a lot of physics all happening at once.
It sounds tricky enough to make a single crystal. So what does Kenneth think of our challenge to create my own monster snowflake?
If you want to make it look like a snow crystal, an actual symmetrical snow crystal, that's a tall order. So, it took me a long time to figure out how to do it. So I don't think you'll get it between now and Christmas, but I'm curious to see what you end up with.
It turns out making snow from scratch is much harder than I anticipated. I don't have a lot of time, but I do have access to the University of Manchester's ice cloud chamber. Aha! I'm meeting Professors Paul Connolly and Gordon McFiggins. Is the cloud chamber just behind us?
Yeah, we're just about to go in there. We're about to put the sensor in there right now.
Great, okay. They're in the middle of setting up the chamber for a snowmaking run. That large golden instrument is specially designed to image ice crystals as they form. We're at the bottom of the chamber. Above rises a giant metal tube that's 1 metre wide and 10 metres tall. The pressure and temperature can be set to replicate almost any condition in the atmosphere. Paul's lab is at the very bottom of the cloud chamber,
that's right.
and we're now at the very top of it.
That's right. So
This is where it ends, okay.
But it is basically, there are 3 refrigerated rooms on top of each other.
Whilst Gordon and I have been getting our steps in, Paul's cooled the chamber to minus 15 degrees Celsius. That's optimum temperatures to make pretty hexagonal snow crystals.
If you think about how an ice crystal forms in the atmosphere, in the air, you might have a supercooled cloud, and some of those supercooled droplets would freeze. So we do replicate that. That's exactly what we do in the chamber. We add a vapour source. So we've got a boiler at the bottom which evaporates liquid water into the vapour phase and adds that to the chamber. And the ice crystal should grow from the supercooled water that's in there.
Yeah.
And in the bottom we'll see these aggregates of snowflakes.
Right, okay.
That's the theory.
A supercooled cloud, water vapour below 0 degrees. Why aren't ice crystals already forming?
Pure water won't actually freeze at 0 degrees Celsius. It needs a trigger. And these triggers in the formation of ice in the atmosphere are in the form of ice nuclei. So things like mineral dust and bacteria and pollen can be very efficient ice nuclei.
Gordon's research investigates how different atmospheric pollutants affect ice nucleation.
This type of work is essential to understand the changing atmospheric phenomena on a changing planet. We don't fully understand the relationships between natural emissions, human emissions, and the climate system. So the more we understand about it, the more we can relate the weather phenomena to the particular emission sources and the particular conditions that will enable us to understand future weather, climate, hazard, and impact upon the population.
We're ready to make snow. The question is, can Paul's chamber make record-breaking snowflakes?
We need to nucleate the ice.
Oh yeah, okay.
So for that we have this popping device. So I'm going to switch it on.
Oh, I thought there'd be like a cool pop or something.
You can hear it when you're at the top.
I expected to nucleate the snow with particles, but it seems Paul's got a more efficient way to get the water vapour to freeze.
The way that we initiate the ice crystals in the chamber is by using a compressed air expansion. So that's just a small volume of air at the top of our 10-metre chamber where we allow the air to expand, and at some point in that expanded air the temperature drops below this magical temperature of minus 38 degrees Celsius. So that's the temperature in which pure water droplets will freeze. And then we allow those ice crystals to grow and sediment through the chamber. And in that way we can grow the ice crystals much faster than they would grow in the atmosphere. Now we can start to see some ice crystals appearing. Every now and then we see a larger crystal that flashes up.
Yeah.
So you see?
So we've just created some snowflakes in the chamber.
We have, and you can see they're hexagon shape, which is what we'd expect at minus 15 degrees Celsius.
Great, should we go and have a quick look at what we've created?
Let's do that. Oh yeah, we can see lots of ice crystals in there now, and we can see they're falling out of the bottom of the porthole here. And so, put my hand in here, I can pull some of that snow out.
Oh wow. Oh wow.
So we can see that's the kind of snow that we get.
That is definitely very cold snow. We've made bona fide snowflakes, but these little beauties aren't big enough to impress my New Scientist editors. Fortunately, I don't have to travel far to up the ante. Just 3 miles away at Salford University is the Energy House 2.0 laboratory. Hi. Yes, Madeline from New Scientist. Yeah. Thank you. Wow. My goodness. It's massive. It is absolutely absolutely freezing. Like, my fingers are already cold, and the air feels very dry and still. But also just like how crazy big this place is. It features 2 chambers, each over 9,000 cubic metres and big enough to fit 2 full-size houses. This mammoth facility is run by Professor Richard Fitton.
This is a globally unique facility. There's nowhere else like it on the planet. It allows us to play with the climate. So we can go down to -20 up to +40. We can have gale force winds. We can have solar radiation, which is commensurate with pretty much any area of the globe. And all those kind of variables gives us about 95% coverage of the globally populated landmass. So wherever people live, we can more or less get those climates. So we can really say that this is what the weather is now. Let's fast forward 10, 20, 30, 40 years. Is it going to last, basically?
Richard has given me the use of the labs for 1 day. The clock is ticking, so I'm calling in the snow experts to help me out. Hello, Gordon, this is Richard. As well as Paul and Gordon, I'm joined by glaciologist Professor Douglas Muir from the University of Liverpool and Richard's right-hand man, research fellow Grant Henshaw. And Grant has an ace up his sleeve.
And this is our snow machine.
Okay. With a snow machine in our arsenal, we've got to be in with a shot for success.
I love working here because you get to play with all the environmental conditions. You can make it snow in one chamber and have a heat wave in the other.
Grant's team set up for a test run so we can see what sort of snow it produces. It's pretty cool, isn't it? Yeah.
They're raising the boom arm now, and then we'll turn on the machine and start the snow formation.
Oh, this is really exciting. Look down here, you can see it seems to be snowing right now already.
It looks like a very fine snow.
We have snow, but it feels different to the crystals that we saw in the cloud chamber. Oh, it's like sand! Paul catches a sample on a slide for closer inspection. Oh.
When you make snow with a snow cannon, it tends to make snowflakes that are more spherical, and that's due to the way that the snow cannon works. So they're from frozen droplets, large frozen droplets.
It seems the snow machine makes small, round ice crystals, terrible for creating giant snowflakes, but a familiar sight to Doug.
On Greenland, it doesn't just fall out of the sky, it falls down, and then as it gets closer to the ice sheet, the snowflakes get battered by the winds, and they kind of break down into smaller particles. So what you were seeing there, those little particles, was quite similar actually to the sort of stuff that actually ends up making its way onto the surface of the ice sheet.
So interesting. So we've got like tumbled snow crystals.
Yeah, that's right. It gets milled again and again just by the wind. They're called katabatic winds. They just flow. It's the cold air flowing down off the ice, and it just smashes the ice up into these tiny, tiny particles. The research I'm interested in at the moment is actually sort of trying to recreate some of the conditions that you see at the surface of high Arctic ice caps and glaciers, for example, the Greenland ice sheet. And we're looking at the interaction of what happens when the snow melts and the meltwater percolates down through the snow and hits ice layers. And we're interested in what happens next. The glacier ice and the snow and ice that we see preserved on the ice sheets is essentially snowfall. The oldest ice that's been directly recovered and analysed is nearly 1 million years old from the bottom of Antarctica, and by analysing that we are seeing a window into the past. The snow and the ice that created the snowflake, that created the glacier, is actually giving us direct insights into how the world was long, long before there was anyone there to measure it or any instruments there to measure it. So it is a window into our past for sure.
If we're going to stand a chance of making a supersized snowflake, we have to get the ice crystals to grow bigger. Paul hatches a plan.
Using the snow machine, we'll create a super-cooled cloud halfway up the chamber, then create a second cloud above. With any luck, the snow crystals falling through the lower cloud will grow and aggregate into full-blown snowflakes.
We did explore the potential of creating our own snow in our small lab, and it's an extremely complicated process. And so the chances of us actually successfully making any kind of realistic snowflake, never mind a large one, I think are very, very slim.
So I'd give it a bit more elevation because I think it's going to hit that conservatory. Trying to get it so that it flows out freely and doesn't get too high.
It's a lot higher. Let's go and have a look and see if it feels any different. Ooh. I don't know if you can zoom in enough to see, but on my fingers there's collections of spheres. Yeah.
That'll be fine. Excellent.
Yeah?
So let's have a look at that. Yeah, so we can see that the ice crystals there, they're spherical. They're like frozen droplets. They don't look like your typical snowflake. So I can see a frozen droplet which is almost cracked in two. It's got a big crack down the middle of it. So have a look at that.
Oh yeah! Wow. So we're making them smaller though? That is amazing. It's kind of like a yin-yang symbol. Cool. We found a good bit.
Our experiment hasn't worked. Instead of making the ice crystals bigger, we've caused them to shatter into smaller shards. Seeing how hard it is to make snow, I'm beginning to wonder if the alleged record-breaking snowflake could have been formed at all. Using a measuring mat, we recreate the 38 by 20 centimetre monster.
So I'll just pop it on the ground here, and then if we can collect enough snow to get us all the way around here, and then we can have a sense of what we're aiming for. Things you never think you'll have to do for work. So, do you guys think that a snowflake this big is actually possible? I mean, look at it, it's massive.
No.
Why?
I think, well, because something this size wouldn't form in the atmosphere, and a snowflake is something that's forming in the atmosphere. Once it lands on the ground, it's just part of the snowpack. And so whatever they found, you know, it wasn't a snowflake, it was something which had already probably coagulated on the surface once it had landed. I mean, this would do a lot of damage. Your cats and dogs as well would be running for cover.
3, 2, 1.
Woo!
All of that volume concentrated into a sphere.
With time running out, we go back to the drawing board for one last-ditch attempt to make a proper snowflake.
Right.
Paul and Gordon's idea is to create a makeshift cloud chamber. We'll use a kettle to supply the water vapour. But if this is like the cloud chamber back in their lab, how are we going to trigger the ice formation?
If we want to create the pressurised air, what could we use to do that?
So here it is. We've got a drinks bottle, and the idea is you pump air into the drinks bottle, like so. Several pumps should be enough. Okay.
Paul's DIY popper creates the low temperature needed to trigger nucleation.
So we've just created a kind of chute so that the steam from the kettle is kept in a confined area so that it's got more chance of nucleating and interacting with the snow crystals that we formed and hopefully creating a large snow crystal.
The kettle is put into position. Paul bravely climbs inside the chamber.
See the cloud, and I'm just wondering whether I can see anything.
The bottle is primed.
Is that enough?
And then
That's a good one.
Slide. Paul's found a snowflake. Oh, you've got one. Yeah, we've got one. We've got one.
Don't breathe, anyone. There you go. This looks quite pretty, actually.
Oh.
Yeah.
Pretty.
Yeah.
Right, there you go.
Yeah.
It's a bit of an angle, but you can see it.
We made a snowflake. Oh, yeah, we have. It looks like antler horns or like a bit of seaweed. It looks like ice seaweed.
I didn't anticipate looking down a microscope for the world's biggest snowflake.
Who needs snow machines when you've got a kettle and some tarpaulin? Look, that is really beautiful.
Wow, well done.
Guys, I'm so excited. Yeah.
So we haven't made the world's biggest, but we're on our way to making larger snowflakes. I think the snowflake that we made is pretty enough to go on a Christmas card.
And that's
Just by being in this environment, being in minus 18 for quite a long time, we've all come away with a kind of appreciation for the remarkable conditions that nature combines to create these beautiful structures that we all know as snowflakes, but never really think about how they're actually created.
So how's today been? What do you think we have achieved?
Combining Douglas's knowledge, Paul's knowledge, Gordon's knowledge, mine and Grant's knowledge has ultimately got us towards a snowflake. But where we were this morning, we didn't have that snowflake, we had some balls of ice basically. If we had something bigger, then I think we'd be well on our way to making the world's biggest snowflake. Have we made a big step though? Yeah, I think we have.
Well, it's been a long day, and I think what we can confidently say is that it's really difficult to make snow, let alone a really big snowflake. The snow crystal that we did make was really beautiful and I think deserves a spot on any Christmas card. After all that physics and all of that learning, it's just a reminder of how magical it really is when snow does happen to fall, especially if it falls at Christmas. And from everyone at New Scientist, a very Merry Christmas.